Welcome everyone. So, in today's class, we are going to discuss some results about covering spaces. So, let us recall the result that we have proved during the computation of the fundamental group of circle, namely the lifting lemmas. So, I have combined both the lifting lemmas, the path lifting and homotopy lifting into this one result. This is primarily homotopy lifting, which can be stated as path lifting by restricting the t interval being constant. Okay. So, what lifting lemmas typically says is the following: whenever I have a covering space from E to B, covering map from E to B with some base point here and some base point here, then the point is whenever I have a path at the bottom starting at B0, here I am drawing a loop, but in general any path I can get a lift which is starting at E0. For every lift of the point B0 I can do this construction, okay. And once I fix one of the lifts of B0, say E0, this path is unique, this lifting path is unique. And similarly I can do the same thing for homotopy also. So, in particular, if I have a path homotopy from some space x to my base space here, I can lift the entire homotopy to my covering space, okay. And this lift is also unique provided I give you the initial lift of the path. If it is a path lift, it is a homotopy of paths, and if I give you the initial path at time t equal to 0, then this lifting is unique. And path lifting tells you that if I give you the initial point of the path, then the first lifting is unique. So, therefore, in some sense this lifting is also unique given that I know what is happening to the point 0, 0. Okay. Now, using this we can define what is called the covering correspondence, which is the following. So, I define a map from the fundamental group of the base space to all the points in the inverse image of my base point B0 by the following: phi of a loop goes to f tilde of 1, where f tilde is the unique lift which starts at E0. Okay. So, what you do is, you know that once I fix the lift of the base point B0 which is say E0, then every path which is here lifts uniquely to a path which starts at E0. So, therefore, I look at the end point of that path and I know that if this is a loop, then the end point of that loop will go to the same point which is B0. Therefore, the end points of this path which is the lift of a loop here are all preimages of the base point B0. Therefore, the end point of the path must lie on P inverse of B0. Okay. And therefore, I can define this map which is phi of a loop goes to the end point of the path which is a lift of the loop. Okay. And so, I have a map from the fundamental group to P inverse of B0. This is just a set map. Okay. So, left hand side, although I have a group, this map does not have any property, and we have seen some property of this when this map is injective, surjective and so on. Okay. So, now the theorem that I want to state is the following, that suppose I have a covering map P from B to E which takes E0 to B0, then the corresponding induced map on the fundamental group is injective. Okay. That is the first result. If I have a covering map, then the induced map by the covering map from the fundamental group of top space to the bottom space, this map is injective, it is an injective homomorphism. Okay. This is the first result. Secondly, now if I look into the, so this is an injective homomorphism. So, in particular the image of P star I can think of as a subgroup of the fundamental group of base space. So, suppose H is the image of pi 1 of E0, then I have a set map from the set of all right cosets of H in fundamental group of B to P inverse B0. Okay. I always have a map here. So, the covering correspondence tells you that I have a map from here. What I am claiming here is I have a map from the coset itself, set of all cosets to this set right hand side, which is the inverse image of B0, and this map is injective. This map is always injective, and also this map is surjective when E is path connected. Okay. So in particular, if E is path connected, then this map is actually a bijection. Okay. Therefore, I can identify the inverse images of a base point with the cosets of this group. So right hand side is a topological set, it is a set of points in your space, in the top space, and left hand side is set of cosets which are algebraic objects. Okay. And thirdly, I can actually explicitly describe what this image looks like in terms of topology, in terms of pictures, which says that if F is a loop on my base space at B0, then the corresponding homotopy class, the corresponding homotopy class of the loop, it belongs to the image of P star if and only if lift of this loop is again a loop. So lift of a loop may not be a loop in general, lift of a loop however will be a path, but here I am saying that if the lift of a loop is again a loop at E0, then these are precisely the element which lies on the image of P star, on the image of the induced homomorphism by the covering map. Okay. So let us first see the proof of the first result, which is the map induced by the covering map in the fundamental group level is injective. So to prove it, what do we have to prove? We have to show, so first of all, P is a map from my covering space E, let us write down E0 to BB0, and therefore I can get P star which is from the induced homomorphism from the fundamental group at E0 to the fundamental group at B0. Okay. Now I am claiming that this map is always injective. So to show that, what I have to show is, if I take any element from here and if I look at its image under this homomorphism, then if it is trivial here, if it is trivial element here, and remember the trivial element on the fundamental group are just the constant loops. Okay. So in particular, if it is trivial here, if it is the constant loop at B0, then I have to prove, if I want to prove that P star is injective, I have to prove that this gamma, homotopy class of gamma, is also trivial. Okay. And how to prove that? Well, the idea is, because the projection here is homotopic to the constant loop, by the definition of this induced homomorphism, I know that this is nothing but P composition gamma, and this I am claiming is the constant loop. So therefore, there is a homotopy which takes this loop to the constant loop, and homotopies can be lifted. And it is also unique by the lifting lemma, homotopies can be lifted, and it is unique once I tell you the initial point. So in particular, if I look at the lifting homotopy between them starting at E0, there is only one lift. Okay. But now the thing is, if I look at the constant path, its lift is always a constant path. Okay. And because of, and now again you can use the uniqueness of the lifting, which tells you that if I look at the lift of this constant path starting at E0, it will be the constant path at E0. Okay. And therefore the lift will have a homotopy between the lift of this, which is gamma tilde, and the constant path at E0, which is precisely what we want to show. Okay. So let me write it in words. So if P star of gamma tilde is EB0, so let me be consistent here and put it gamma tilde. Okay. So if P star of gamma tilde is EB0, then you consider gamma, which is the projection of the curve, and then gamma is homotopic to the constant loop via some homotopy. Lift this homotopy. This will give you a homotopy between the lift, which is gamma tilde, and the constant loop. Lift of a constant loop is again constant, right? So therefore I get a homotopy between these two loops, which is lift of gamma, which is gamma tilde, and the constant loop. In particular, gamma tilde, the homotopy class of gamma tilde is constant. Therefore gamma tilde is trivial, therefore P star is injective. Okay. Now let us go to the proof of the second lemma, second part of the lemma, which tells that I have a set map from set of all right cosets of the image of P star to P inverse B0. And what is the map? The map is, if I look at a right coset, then send it to the end point of the lift of this element alpha. Okay. Now, I know that once I fix the initial point, which is E0, every path lifts to a unique path starting at E0. Therefore, there is only one lift alpha tilde of alpha which starts at E0, and I am sending the map, sending the element which is right coset of alpha to the end point of alpha tilde. Okay. So, remember our covering correspondence has the map from the fundamental group of B, B0 to P inverse B0, and here I am saying that I am getting the same map, but the map is not only as from the set here to here, it actually factors through the coset, through the subgroup. Okay. So, first of all, I will show that if E is path connected, then this map is surjective, and then I will show that this map is in general injective. Okay. So, first of all, if E is path connected, then if I take any point in P inverse E0, so let me draw the picture here. So, let us say this is E0 and this is another lift of B0. Okay. So, in particular, if I take any point E1, which is lift of P inverse B0, which is one of the lifts of B0, then I have a path, because E is path connected, I have a path, and once I project this path here, because both E0 and E1 goes to B0, this will form a loop. Okay. This will form a loop, call this alpha, and if I look at lift of alpha starting at E0, because of the uniqueness, it has to be alpha tilde, which is the path that I have chosen from, and therefore, alpha tilde of 1 is exactly E1. This is exactly alpha tilde of 1, and therefore, if I look at the right coset corresponding to alpha, then this must go to E1. Okay. E1 of let us say, yeah, which is alpha of 1. Okay. Now, to prove injectivity, what do I have to show? I have to show that if I take two cosets H alpha and H beta, then they must go to the same element under this map, under this correspondence. Therefore, the corresponding endpoints of alpha tilde and beta tilde should match. That is what I want to show. Okay. So, suppose T of H alpha equal to T of H beta. Therefore, what do I have here in particular, that so I have this, so T of H alpha and T equal to T of H beta implies that alpha tilde 1 equal to beta tilde 1. Therefore, I get this paths alpha tilde and beta tilde, which both starts at E0 and ends at the same point. Their end point beta tilde 1 equal to alpha tilde 1. So, they ends at the same point. Okay. So, in particular, I can consider this loop which goes via alpha and come back alpha tilde, come back via beta tilde. I call it alpha tilde and beta tilde bar, which is the inverse element, and that forms a loop at pi 1 of E comma E0. You consider the homotopy class of the corresponding loop, then the corresponding map induced homomorphism, take this to H, because H is the image of the loops, of the homotopy classes of loops based at E0, and this is one such loop which is based at E0. Okay. So, in particular, P star of this thing is in H. Now, if you apply P star to this element, this is nothing but P compose alpha tilde star beta tilde bar, which is nothing but alpha star beta bar, okay, which belongs to H. This implies that the coset, the right coset corresponding to alpha and beta are exactly same, H alpha equal to H beta. Okay. Right. So, let me recall the statement again of this proposition. It says that the map, the homomorphism induced by the covering map, namely P star, is firstly injective. Secondly, if I consider the corresponding covering correspondence which takes an element in the fundamental group of B and send it to the endpoint of the unique lift of that element starting at E0, then that correspondence factors through the subgroup which is the image of P star, and this map is actually bijective provided E is path connected. Now, to prove, the only thing that is left to prove is the C part, which says that if F is a loop at B, which is at B0, then I know exactly what it looks like, what are the elements of the image under P star looks like, and these are exactly loops whose lifts are also loops at E0. So, how do we prove that? So, firstly, if gamma is a loop based at B0 such that gamma tilde is a loop at E0, then definitely its projection P star of gamma tilde, which is nothing but P composition gamma tilde, is gamma. Therefore, definitely gamma is in H. Okay. Now, conversely, suppose gamma is in H such that gamma is P star of gamma tilde, okay, then such that they are in the same homotopy class. Therefore, there is a homotopy which takes P star of gamma tilde to gamma. Okay. Now, this is a homotopy, lift the homotopy, I get a unique lifting of this homotopy starting at E0, and that immediately that lifting will be a that lifting of this homotopy will be a lifting between gamma tilde and something, and that something is again a lift starting at E0. Therefore, and this homotopy is this lift is a lift of a homotopy, path homotopies. Therefore, the endpoints are fixed. So, in particular, the lift of gamma that I am going to get will also starts at E0 and ends at E0. Therefore, that particular thing will have a lift which starts at E0. That is the proof of this proposition. Now, let us see how we can use this proposition. This proposition is useful in many contexts. So, let us discuss something which is called the sheet of a covering. So, suppose P from E to B is a covering map, okay, and you take an evenly covered neighborhood, okay, then the open sets P inverse U are projecting homeomorphically to U. Okay. So, P inverse U will be disjoint collection of open sets, each of them are projecting to U. Okay. And each of these open sets which homeomorphically projects to U are called sheets. So, you can think of them as the layers or sheets which projects directly to U. Okay. Now, as P inverse U is a disjoint union of sheets, number of sheets are of same cardinality for any x in U. Okay. So, why is that true? So, first of all, P inverse U is disjoint collection of sheets, let us say U alpha. Okay. Now, if I take an element here x here, then P inverse x, each element of P inverse x will lie exactly in one of these things, and therefore, and because this P is a homeomorphism from U alpha to U, therefore, each U alpha must contain at least one of the preimage of x. Okay. Therefore, the number of elements, the number of sheets corresponding to a evenly covered neighborhood is exactly the number of a point, inverse image of a point in one of these evenly covered neighborhood. In particular, if x is in U, then number of elements in P inverse x is exactly the number of sheets of P inverse U or U. Okay. And you can see that, okay, this is true, this is equal for all x belongs to U. Therefore, this number of elements in P inverse x in particular is locally constant. Okay. Now, and this goes into a discrete set, the cardinality goes to a discrete set, it is just set of all integers which is a discrete set with its usual topology. And so, therefore, this map, it is a locally constant map, and so you can show that this is a continuous map also, because it is a locally constant map anyway. So, if it is a locally constant map, if E is path, if x is path connected, then if E is path connected, then it's if B is path connected, then if it is a locally constant map, then the map is also globally constant. In particular, if B is path connected, let us say B is path connected, although it is true for connected also, but let us be specific. If B is path connected, then for every x, P inverse x has the same cardinality, and that sometime also called the cardinality of the sheets or the number of sheets. If it is finite, we call it number of sheets. If it is infinite, also sometimes we call the number of sheets of the covering. Okay. So now, using our previous proposition, we can associate number of sheets of a connected covering space and the corresponding cosets of the image of P star. And so the corollary is, so we know that there is a one-to-one correspondence between number of right cosets of H, which is the image of P star, and the number of elements in the inverse image of P inverse of a point, of a base point, and therefore this is a bijection if B is path connected, and therefore I have the following statement that if P from E to B is a covering between path connected spaces with P of E0 goes to B0, then the number of sheets is actually equal to the index of the subgroup in here. Okay. So, in particular, this you can use to the following setup. So, suppose I consider the map from S1 to S1, which is Z goes to Z to the power n, and this you can check is a covering map. So, check this is a covering. Okay. So, now because this is a covering, I get a corresponding induced map which is, let us say, P, which is P star, which is from pi 1 of S1 to pi 1 of S1, and this map exactly is 1 goes to n, okay, which is one loop going to the n times of the loop. Okay. And this matches because if I look at the image of Z inside here, this will go as NZ. NZ is an index n subgroup. Okay. And using this we can actually prove a lot. In fact, we can prove, so for example, we can show, and I will give this as an assignment. You can check this, for example, RP2, which is a two-sheeted covering from sphere, so which has a two-sheeted covering which is sphere, and sphere is simply connected. So, in particular, the fundamental group of RP2 will be group of order 2, which is just trivial element and 1, Z2. Okay. So, you can check this thing. Okay. And so, the next result that I want to say is the, so okay, before going into the next result, let me just repeat what I have just said. So, in particular, I can see that I can use this result into the following format that let us put it here. So, if I have, let us say, if I consider the map, so this is an example. So, let us look at the map from S2 to RP2, okay, which is the map X goes to the equivalence class of X, which is X is equivalent to minus X, okay. And if I do that, then I can do the following that corresponding map. So, this is, let us say, P, then corresponding P star is fundamental group of S2 to fundamental group of RP2, and you can check this is covering. So, check, so P is covering, okay. And now this is trivial group. So, the question is, what is this group? Now, I know that whatever this group is, the index of the trivial group inside that group is 2, okay. And so, the only group where index of the trivial group is 2 is the group of order 2, okay. So, this would imply that the corollary would imply that the fundamental group of RP2 is isomorphic to the group 2 elements, which is Z2, okay. And we can use similar kind of techniques to say various things about the covering groups to the spaces of the fundamental group of covering space, okay. Now, let us see something which is slightly related to these results, but in a slightly different way of expressing the things that we were discussing. So, the first thing that we noted in this discussion is that if I have a covering map from E0 to B0, then the corresponding map P star is injective, right. So, therefore, every covering space and fundamental group of covering space E0, I can think of sitting inside the fundamental group of BB0 via the map P star. Okay. It is injective, so I can consider the image as a subgroup, okay. And so I can identify the fundamental group of the top space as a subgroup of the fundamental group of the bottom space. Now, a general question, a normal question is, okay, this construction is quite natural. Once I have a covering space, I get an injective map and I can identify it with the subgroup of my base space. Now, the question is the converse true? In particular, if I give you a subgroup of your base space, fundamental group of base space, is that the image of a space which is a covering space? Okay. So, let me ask the question. So, question, suppose I give you any subgroup H is a subgroup H is any subgroup, okay. So, question is, does there exist a covering map P from E0 to BB0 such that H is exactly P star of the fundamental group of E. Okay. So, the question is, if I give you, so first of all we have seen that if I have a covering space, then the image of the fundamental group I can think of as a subgroup of the image of the fundamental group of the base space. So, if I give you some covering map here from E to B, some P which takes E0 to B0, then I can consider the fundamental group of E to be a subgroup of the fundamental group of bottom space. Here, so what I did was, I have a topological information which is the covering map, and from that I got an algebraic information which is the P star, the corresponding homomorphism is injective. Therefore, the image of this is a subgroup here, okay. So, I can treat this top space, fundamental group of top space as a subgroup of the fundamental group of bottom space. Now, my question is, can I go the other way around? If I start with an algebraic subgroup, simply a subgroup from the bottom space, okay, can I consider it, can I construct a space E such that P star of E is exactly this subgroup, okay. And so, now if I be very specific, in particular if this has to be true, first of all this has to be true for trivial subgroup, because any group contains trivial subgroup, okay. So, a sub question of this would be, so let me put this as a sub question. So, does it, so if H is simply the trivial group which is the constant loop, is the above true? So, first check, is the above true? So, if it has to be true for all subgroup, first it has to be true for at least trivial subgroup, okay. So, what is the meaning of that? Okay. So, the meaning of that would be that I get a space, let us call it B tilde, and I get a covering map B such that P star of fundamental group of B tilde, let us forget about the base point for a moment, is the trivial map, is the trivial group, okay. So, now P is injective. So, therefore, in particular this would imply that your group itself, the fundamental group of B tilde itself is trivial, okay. Fundamental group of B tilde itself is trivial. Okay. So therefore, what do we have here? That if this result has to be true for all subgroup, at the very least this has to be true for trivial subgroup, and if it is true for trivial subgroup, I would be able to construct a space whose fundamental group is trivial. Okay. And so now in particular, if I assume that it is path connected, then this will be a simply connected space. Okay. So therefore now the question is, if I give you a topological space, can you construct a space which covers that given space and whose fundamental group is trivial and path connected? So that kind of space would have a very specific role. This will play a very interesting role, as we will see, and these are called the universal spaces corresponding to topological spaces, and we will see how to construct a universal space of a given topological space. Okay. Now, one of the results that I want to discuss is of the following form, which is the fact that, okay, I have a covering space, and let us say, so suppose I have a covering space from E to B, which is given here. Now, I know how the image of the fundamental group of this looks inside here. It is an injective subgroup, and I know exactly if I specify the base points here, then the loop which are here and which are in the image will be exactly those which admits a loop which starts at E0. Now, if I want to generalize this and I want to ask, okay, if I give you an arbitrary function from some space x to here, which let us say takes x0 to b0, when does this map admit a lift? Okay. And so the theorem states that if P is a covering space and F is any map, okay, from a path connected and locally path connected space, okay, then F admits a lift F tilde if and only if the induced map by F in the fundamental group lies exactly inside the image of the fundamental group induced by P. In particular, you can think of it like this. If I am only considering this covering side, I have a covering map, and this induces a covering homomorphism which is injective. So therefore, I can think of this fundamental group as a subgroup of the fundamental group here. So therefore, this map admits a lift F tilde if and only if the subgroup that goes inside here via the map F lies inside exactly the subgroup which comes from top. Okay. And so the algebraic information is enough to conclude a topological information, which is the existence of a lift. Okay. So again, it says that if I have a covering map P from E comma E0 to B comma B0, then given any map F from X to B, where X is path connected and locally path connected, and we will see why we need this criteria, then this F admits a lift if and only if, in terms of the algebra, if I look at the algebraic side of this picture, namely if I look at this P star, F star and the corresponding fundamental group, then all I have to make sure is that F star of this fundamental group goes inside here. Okay. Now, one side, so how do we prove this? So suppose F tilde exists, suppose such a lift exists. So then clearly, if this exists, then if F exists, then if I take a loop here, then under F I will get a loop here, but this lift exists, so I will get a loop here which projects here. So in particular, this loop always lies in the image of the top loop, and therefore this condition is always satisfied. Okay. So if the lift exists, then we clearly have that F star is P composition F tilde whole star, which is sitting inside P star. So therefore one side is clear. If such a lift exists, then the subgroup should maintain this inclusion. Okay. So, we have to prove the other way around. Suppose the subgroups maintain the inclusion map, I want to construct a leaf. So, how do I construct a leaf? The only way I can construct it, at least the natural way to construct a leaf is the following. See, on the left hand side I have the information on the fundamental group, which is just the loops and homotopy classes of loop. I want to construct a map from X to E. Okay. Here things are points. So, if I want to go from points to loops, from loops to points, the only path, at least the natural path I have, is to consider paths and their lifting. Okay. So, the idea is, if I have any point here and I want to see what its image is under f tilde, what I do is I consider a path between these two, and then I take it a path here. Okay. Now, it is a covering, so this will have a lift, unique lift, which starts at E0 and it ends somewhere. Okay. And so, I send this point here, end point of this path, to the end point of this unique loop. Okay. That is a natural way to define this map. Okay. So, for using covering correspondence. So, that is how we define it. We define f tilde from xx0 to E0. So, let me draw the picture here again. So, it will be easier for you to understand where the spaces are. So, this is E to B and this is X here. So, here you have B0, you have E0, you have X0. So, if X is there, you take a path gamma and then I look at F composition gamma, this ends somewhere, and then I look at F composition gamma tilde, and then I send it to the end point of F gamma tilde. Okay. So, F tilde of X should go to F composition gamma tilde of 1, where gamma is any path from x0 to x. Okay. And F composition gamma tilde is the lift, it is a unique lift. Every path has a unique lift, provided I tell you the initial point. So, here the initial point is E0. So, there is a unique lift. Okay. So, now there are multiple things here. First of all, this depends on the path that I am choosing. So, therefore, I have to show that the definition is independent of the path here. Okay. Then only this f tilde will be well defined, and the next part will be I have to show that this is also a continuous map. Okay. This is indeed a lift and it is a continuous map. So, let us see one by one. So, first of all, if gamma prime is another path from x0 to x, so let us say gamma prime is another path, then again the idea is similar to what we have done. If gamma prime is another path, then the composition of gamma and gamma prime bar is a loop at x0. You look at its image loop, which becomes a loop here, and you look at it lifts. Okay. So, if gamma prime is another path from x0 to x, then you consider the loop which is gamma star gamma prime bar, okay, in the fundamental group of x0. Now, I use the hypothesis that the image of this fundamental group under f star lies inside H, which is the image of the fundamental group under P star. Okay. So, this f star of gamma composition gamma prime bar, which is f composition gamma star f composition gamma bar, this lies inside H, P, this is just simply H. Okay. This lies inside H, which is simply P star of the image of P star. Okay. So, therefore, if I look, this path lies inside H, and I know exactly what are the elements that lies inside H. I know the elements which lies inside H are the loops which lifts to a loop based at E0. That information I already have from our previous discussion. So, therefore, if I consider this path H, I call it H0, this path admits a lift starting at E0, admits a lift which is a loop starting at E0. So, therefore, there exists a homotopy H0, Ht to a loop H1 such that H1 admits a lift which starts at E0. Okay. So, now look at that lift of H1, which is, so H1 is homotopic to H0, H1 admits a lift which is called H1 tilde, which starts at E0. Okay. Now, if you look at ht tilde, the homotopy that takes h0 to h1, I consider the corresponding lifting of the entire homotopy. Okay. So then this ht tilde, ht gives you a lift ht tilde, which is a lift of h0 tilde, okay, right, and h0 tilde is a lift of h0, which is a loop at e0. Okay. Now I know that the lifting are unique. In particular, if I look at this lift of this entire thing, okay, this will go from E0 to another endpoint of P inverse of B0, and then the rest of the path will again come back to here, because this composition loop is a loop based at E0 and these are also path homotopic. So, the endpoint of this path and this path should be same. So, in particular, by the uniqueness, F tilde composition gamma should be F composition gamma bar tilde, which tells you that this F tilde is well defined. No matter which path you choose, the endpoint should be same. Okay. Now, to define continuity, what you have to do is the following. So, suppose, so I have defined F tilde in terms of path lifting, right. Now, what happens is, if I am focusing on an evenly covered neighborhood, in an evenly covered neighborhood, P is homeomorphism corresponding to each of its preimage. Okay. And so, if I take a base point B0 and look at a neighborhood there, then its inverse image will split into open sets and each of them contains one inverse image of B0. So, if I specify which B0 inverse image I am talking about, there will be a unique one-to-one homomorphism, and in that map F, which goes from my space X to that open set U, there I can construct the lift just by putting P inverse. Okay. Now, to check that F tilde is continuous, all I have to do is to make sure that F tilde maintains or agrees with this construction locally. It should agrees with P inverse, and then automatically the continuity of P inverse locally will tell me that F tilde is continuous. Okay. So, suppose U is an evenly covered neighborhood of Fx, let us say, and F tilde of x. So, I am, the point is I have here, here and here. Okay. So, I take a point x here, so I get Fx here. I take an evenly covered neighborhood which is U here, and so there exists an evenly covered neighborhood F tilde which has Fx tilde. Okay. And so, this is a local homeomorphism. Okay. Now, because this is local path connected, because my space is locally path connected, okay. So, then if I look at this evenly covered neighborhood, I look at its inverse image, okay, that will give me a neighborhood around X, some neighborhood, and because it is locally path connected, this is where I am using locally path connectedness, I will get a path connected neighborhood here which is V, which goes inside this evenly covered neighborhood. Okay. So, therefore, by local path connectedness, this is where I am using that I get a neighborhood here V which goes inside this evenly covered neighborhood. Okay. So, by local path connectedness, there exists a path connected neighborhood V of x such that this goes inside the evenly covered neighborhood. Okay. F of V is inside U. Now, what happens is, if gamma prime is any path from x0 to, let us say, so this is, let us suppose this is my point here, this is x0, this is x, and this is your V. Okay. And so, if gamma prime is any path, so let us say gamma prime is any path from x0 to x prime. Okay. So, if gamma prime is, let us say, any path, so let me draw this picture a little bigger so that understand it better. So, what happens is, if this is, let us say, x0, this is x and this is V. Now, if I take any path from x0 to some point x prime, okay, what I can do is, I can fix a path gamma from x0 to x, and then for any other path eta from x to x prime, I will get a path from x0 to x prime. Okay. So, for any path gamma from x0, so for any path gamma prime for x0 to x prime, we can consider a fixed path gamma from x0 to x and then another path eta from x to x prime. Okay. So then F compose gamma star F compose eta is in B. Okay. This path which is, I now look at B, this is a path, okay, and therefore this path lifts. So every path there is a lifting, so this path lifts. Okay. Now if I look at the lifting of this path, what will I have is the following. If I start at E0, I am starting the unique lift at E0. So this path lies entirely inside U. If this is the image of, this is eta. So if I look at F composition eta, let us say I am looking at, this is eta, I am looking at F composition eta, F composition eta, and this sits inside U. Okay. And U homeomorphically lifts to U tilde. So therefore this I have F composition eta tilde, which is nothing but P inverse of F composition eta. Okay. Because this is a loop inside my evenly covered neighborhood. Evenly covered neighborhood is a homeomorphism to the top space. I am just inverse imaging it. Okay. It's taking the inverse image. So F compose eta tilde is P inverse of F compose eta, and P inverse is an inverse of a homeomorphism, therefore it is continuous, right. Therefore what I get is this F tilde of V, this any V that I am taking, this is for any point, this is true. So in particular this thing is always going inside F P inverse of U, which is U tilde. So in particular F tilde of V is goes inside U tilde. So therefore if I take a neighborhood of a point in the top space, its inverse image is lying inside an open set. It is like a inverse image of an open set is open, because if I look at F tilde inverse of image, inverse image of this U tilde, then every point has a neighborhood which goes inside U tilde. Okay. So and because F tilde restricted to V is P inverse of F, therefore this map in this F tilde goes from V inside U, and on the restriction, this F tilde on the restriction of open set, it is basically a continuous function. It is a composition of P inverse with F, therefore F tilde itself is continuous. So we have constructed a continuous lift, and we have seen that this lift exists whenever the image goes inside a simply connected space. Okay. So one of the application of this comes in complex analysis. Let me briefly discuss this. So if you look at C to C star, which is, let us say, let us write C minus 0, I have a covering map which is Z goes to e to the power Z. However, this thing do not have trivial fundamental group. This is C minus 0, which is R2 minus 0, which deformation retracts to circle whose fundamental group is trivial. However, if so therefore if I look at the identity map from C minus 0 to C minus 0, this does not lift. This does not lift. However, if I remove an entire line, so what I can do is I can remove C minus, let us say, the negative x axis, C minus infinity to 0, then this is homeomorphic to the upper half to a simply connected space. So this C minus this entire line, this is simply connected, therefore this has fundamental group trivial. Okay. And so okay, let me say this thing again, right. So this thing has fundamental group trivial. So in particular this thing has fundamental group trivial. So if I am looking at the induced map, this goes to the trivial group, which is exactly C has a fundamental group trivial. So it sits inside pi star of A. Therefore this identity has a lift. So this identity admits a lift, which is identity tilde, and which tells you that if I look at, so this map from C minus 0 to C, this has this property that if I go to So, call this let us say f. So, then f z e to the power f z is z, which tells you that f z is log of z for if z behaves like log of z in terms of things. So, at least for if I remove this negative x axis, I get at least one lift of exponential, which is one branch of logarithm, and now I can choose any subset of C such that C minus that subset has trivial fundamental group, and I can construct one lift. In particular, I can construct some inverse of exponential map based on what I am removing, as long as the complement has a trivial fundamental group. Okay, thank you.